It's
It's
one,
less.
not one.
It's 100 times less, isn't it? And if we could divide I by 100, then the power lost would be a 10,000th of what we'd lose if we didn't do that. So the more you can lower the current when you transmit the power through the wires, the better. And this is the device that can do that. So this is why you want to do that. You know, anybody know what this thing is called?
Inductor.
Transmitter.
Transformer. Yeah,
Transformer.
Oh, I was
Well,
actually transmitter sounds.
No, not quite. Transformer takes low voltage, relatively high current power, in this case, and steps it up to very high voltages and low current. Same amount of energy, but just different kind or different form.
but why do they, wouldn't you only need like one of those, so right by the source of energy? Because why is there some like everywhere?
Well, here's the deal.
Because it needs to be.
Then it goes to your house, right? It goes across the countryside, nice, high voltage. When we get to your house, do you want 250,000 volts in the electrical plug?
Yeah.
I would rather not. Just
No,
just for
more
that.
current.
So what do we have to do when we get over here?
Transformer
Raise
back.
We have
Raise
to
the
change it
current.
again, right? So instead of the kind of transformer we had before, now we're gonna have lots of coils. And then right next to it, we're just gonna have a few. And what that's gonna do is step down in the United States in the case, and sometimes this is done in 2 steps instead of just one. Step it down from hundreds of thousands of volts to about 120. And step it down, what's gonna happen to the current?
Because
It's gonna go back up so you have enough current that you can use to run your hairdryer or whatever you want.
So the
why
low
does the current
current
go back in?
leads to
Because the power has to stay the same. Go ahead, then I'll
low
answer.
low current that leads to like higher efficiency or it's like
No,
you
no.
lose less.
It's just, yeah, if the current is low, in a way it's more efficient because you don't lose as much
Yeah.
anyway.
Okay.
Powers
What is
the,
the whole
powers
system
the energy,
Good.
Power is the energy you're sending to your house per second.
and so, but the powers, like, it still goes down by the time it reaches.
In
you.
reality, it's gonna go down, but it's not gonna go down
Near as
when you
much.
go from here to here. At least it shouldn't. Now, inevitably there's like friction, so there's gonna be some loss, but the big loss is in the wires on the way to your house.
So what is this whole system called?
This is our power network, I guess.
Okay.
Yeah. But we have a generator that makes the power to begin with, either by burning fossil fuel or something. And then we have the transmitting system getting into your house.
Okay.
And then we have to get it down to the level where it's still safe.
Why does B1 have to equal B2?
Because energy is conserved. So you're not doing anything here to lose energy. You're doing it here in the wires, but not in the transfer.
But like, that's a direct transfer, even though it's just like
Yeah.
through a magnetic field.
Yeah. So, did I answer your other question too? Do you remember what it was?
I think it was
Yeah.
along the same line. Yeah.
Okay. That's,
So, like you just said, so like power P1 equals P2, like between the coiled wires, but then across, like
but when it's traveling along here,
along there, it's
then power is gradually decreasing because you're losing energy by radiating it out in the countryside. And then you get to your house, and instead of increasing the voltage, you want to decrease it. So this is called a step down transformer.
So the other one is step up transformer.
Yes. And this one steps the voltage up. We're talking about what you do to the voltage.
One time at Kincaid, we were playing lacrosse, and it was kind of like stormy, and then there's like a power line across like the field,
Yeah,
and the transformer just exploded.
it looks like fireworks,
Yeah.
right?
Was that
It's
last year?
gorgeous.
Yeah. It was
empty.
no.
I was
It
driving
was on
down
the
Bel Air
close
Boulevard, one day, and I'm here, right across the street, a transformer exploded, and
It
it's
sounds like
absolutely
a
gorgeous,
bomb going off.
I almost ripped my car, I mean, it's just like, whoa, but it was really kinda cool.
I remember because like right when it went off, I like shot and then it and it was like a bomb.
Yeah.
So that's like
Usually
what
that's
happens.
So
because
loud.
it's struck by lightning.
It's so cool.
Or like when
Yeah,
power
it was-
lines
the
come
sparks
down,
went
there's like
everywhere.
happens in movies or whatever, the
Yeah.
sparks, that's what it is.
Yeah. It's like a waterfall, but it sparks. It's not,
Yeah.
It's classic.
I think we're kind of like, alright, we're done for today.
that would be the one I kind of took cover, I think. It'd be smart to do that. Okay, and then when it gets to your house, you can use it, and in reality, usually there's a step-up transformer near the power company, and then they go to a main place where it's like out in the country, and they have it, and then they really step it up, okay? They take it cross-country, those big towers, and then when it gets near your house, like near my house, Newcastle and West Park, there's a big old electrical yard, and a lot of towers and stuff like that. And that steps it down some, and then when it gets to your house, they step it down the rest of the way. And your house gets two kinds of power, it gets 120 volts and it gets 240 volts. And the 240 volts are for the air conditioner and the, if you have an electric dryer and the oven and stuff like that, and the 120 volts are for wall outlets. Okay?
Oh, so the things with towers and stuff, those are just like.
Those are basically transmitting towers, and they have to keep it really, really high so that some poor idiot with a rake can't touch it. Because what happens, if that's 150,000 volts,
Get electric.
and you happen to touch it, and you're standing on the ground, which is at zero potential, what happens to you?
Your toast.
Yeah,
Wait, so how does it?
Literally.
What's the
You
air?
are literally toast.
what air?
Unless you
You
wear
said
rubber
that
soles.
if you're in the air, what if you're jumping and you do
Rubber soles.
Yeah.
Well, you had the problem about the bird standing on the power lines.
yeah.
Even if the power is, the voltage is really high, if the bird is standing here and here, there's so little resistance between his legs that there's not much of a potential difference between his legs, he doesn't get a shock.
Sounds like a squirrel.
But if you're hanging from a power line and your foot happens to touch the pole, which is at zero potential,
Ouch.
that's a big potential difference. And every once in a while, you'll see a squirrel who was, his tail touched the tree while he was running along the power lines. And we have fried squirrel.
Wait, so if you don't have like a
Let me
power
scratch
line like
first.
right next to your house, how does it get like directly from like the street?
There's power lines coming into your
Oh,
house.
like
Don't want
underground?
a pot.
Maybe, or in my neighborhood, it's from poles that run down in between, down the middle of the block, in between the house on one side and the house on the other side.
Okay.
There are power lines that run down, and they come from those lines into your house.
Okay.
So wherever your electrical box is, that's where the connection is.
Okay.
Okay, so, and the whole deal is, most appliances, like computers and anything that has any kind of information in it, can't use direct current, or alternating current. It just fries their little brains. Okay? So when you have a computer, you have to somehow change the alternating current into direct current.
Is that what the little box does?
No, the little box. What's in this little box now? You know. See? Because what does this box do? This box plugs into 120 volts. And it doesn't hurt my computer, which takes around 5. So what does this
So
box do?
hold the
Resistor.
bolts and then disperse them.
How do you drop the volts? What do you
You
use?
Step
Step
down
down.
transformer.
Transformer.
So that's what's in here, okay? So it's to change, so you can plug it into the wall, but you won't fry your computer. And then the first thing in your computer, when you connect that to your computer, is a little thing called a rectifier that changes the alternating current into direct current. Okay? A lot of things like ovens and stuff like that, they don't need to change it. Anything that heats something up or something, you just use it. But things, like I said, that have any kind of information stuff, TVs and stuff like that, all have to run on direct current. Okay? So what if a power company comes to you tomorrow and says, "We've got a deal for you.
You take it.
We'll we'll charge you for the amount of energy you use, or we'll charge you a penny per electron that you get from the power company.
Energy.
Oh, yeah, totally.
What are you gonna choose to pay your bill?
Penny per electron, just because it's always the opposite.
Yeah.
Yeah.
Really? So you think you're
I'll
not gonna
feel
pay
good.
for billions of electrons?
I mean, why not?
It's a trick question.
Is he making any sense? If it weren't me, if it were the power company coming to you and asking you this,
You pick the first one.
you'd pick the first one, wouldn't you?
Yes.
How many electrons do you actually get from the power company?
0.
Zero, none.
Bingo, bingo.
Because there's no electrons transferred here, right? All there is transferred here is energy.
So we only get electrons from.
You get electrons that are already in the wires of the appliances that you use.
So you should pick
You should
second
pick,
choice.
you should pick per electron.
the
I know.
It's unlikely to say.
Wait, so what, proton electron?
James, what was your reason?
Yeah, no particles get from the power
Sounds like a lot of
company to
money.
you.
I'm like yelling down
It's just the
here.
electric field
I'm like,
and the
I'm
magnetic.
So there's no protons or electrons that they're giving you. It's just
Right.
like electricity.
They're giving you energy to make the protons and electrons in your wires move,
Mhm.
but they're not giving you the protons. Okay. All right, so now you know a lot more about transmission of power. Now, we're gonna go back to this little video. And watch the rest for a little bit.
Trust you, dirty Russian.
And I want you getting your hands out and limbered out. Okay?
Limber that is. Limber that.
Hands out. Fingers are above the wire.
I'm about to swap it out. You'll agree this
So this wire has a magnetic field that's circular around it, pointing in one direction. Okay. Science kid looks.
I could get these things out and I could show you these, but you wouldn't be able to see them nearly as well as you can see them on the video.
And this is easier.
No, it scared me. I get nervous around wires.
I don't like shocks.
So look at noise. Okay, now this coil is, I'm connecting the positive here, and you can see underneath, it's gonna go up and over like this, right?
So on top of the coil, the current's coming out toward us.
Then you have a coil of wire, like this. Current's going that way on the top of the coil. So I put my fingers in the middle of the coil, and my fingers point toward the camera, right? So if I put a magnet here, without the current turned on, it's like that, and with the current on, it swings around and points towards you.
You see that the blue end of the magnet shows you the direction.
It will. We take a magnet
How did the initial?
and put it up here, you see that it points the opposite direction. So it's sort of, if you can imagine like a donut. almost. Yeah. Okay. What do you think would be the effect of?
Wait, was this last year?
Yeah,
She said Nessa's name.
Because here we
yeah,
have
it
played
was
one more.
Matt Henriksen.
Oh, I heard Karen Brown.
Yeah, she's there.
Yeah, it would seem like the force is a lot stronger. Now this one, if you look at the way it's wound, you guys over here can see it. It's wound so that it's coming this way,
That's really
right?
good at this.
This is the positive.
Yeah, it is.
Oh, hey.